Okay, I just realized then I changed the arm. I probably put some things off the screen, so let me just revisit this. I'm going to put this here so that you can see everything hopefully again. So again, I'll just kind of briefly mention what I did just so you can put together the pieces. So this is just a matter of writing down all of our information. And I think here we should be okay. Will this lamp help? And it darkens again. All right. So here again, we have this is just a summary of all of our information. We picked up H1 and H2 from table A22. I think you should have been able to see everything with the possible exception of the final answer, which is 330 kilojoule per kilogram. Whether we do it this, I'm sorry, that's not the final answer, that's the change in entropy. So 301 kilojoule per kilogram or 300 kilojoule per kilogram, depending on the method. All right, for part B, what would have been cut off? Just the very end of the plugging in, I think. So you may not have been able to see this piece where I was plugging in, but again, the idea here is to start with the entropy rate balance equation. Divide through by m dot. That means we know everything. Here we're going to use this equation. We can also substitute this part with the S zeros from table A22. And now we're just dropping in all the pieces, getting a final answer. Okay, so hopefully I will be, I'm going to go check before I get started here and make sure that I'm actually on the board. Okay. So I'm not going to move anything this time. I'm going to leave everything this way. Okay, so let's take a look. Heat exchanger. So here is our last problem. It's a heat exchanger problem, so that means lots of writing because that means we have two flows. And so we're going to have 2 inlets, 2 exits, 4 columns, so a lot to write down. Okay, so we have saturated water vapor in a heat exchanger, and we know, what do we know about that? Well, first, here, so let's just see what we know. So we start with water vapor over here. Hopefully you can see that. Water vapor over here, we know the pressure. Okay, and then over here, sorry, trying to make sure I can see everything. So, and then I know at the exit, it exits at 20 degrees with negligible change in pressure. So that means it started at 1 bar and efficient comes out at about 1 bar. Ambient air at 275 K and 1 atmosphere enter. In a separate stream, and exit at 290. It says 200 in the file on Blackboard. It should say 290. It exits at 290 and 1 atmosphere. And so here we have water vapor, here we have air. I've not written anything here because I don't want to assume I know what state that's in just yet. So we have air mass flow rate is 170 times, where did I write that? Oh, down here. So I left a little space to find enthalpy and entropy. I know that it's steady state, so I don't know what the mass flow rate is, but I know that it's the same for the water vapor, and I know that it's the same for the air, and I know that the air is 170 times as much as it is for the water vapor. What else do I know? Air can be modeled as an ideal gas, good news. Ideal gas, and we know its specific heat. We're going to ignore KE and PE pretty much as usual, and then we know we have steady state. So then the question becomes, for a control volume that is the entire heat exchanger, evaluate the rate of heat transfer in kilojoule per kilogram. So again, we have this because it's kilojoule per kilogram. And then additionally, for an enlarged control volume that includes the heat exchanger and just enough of the surrounding that we can know what the ambient temperature is, then we're going to find entropy production, again, in kilojoule per kilogram Kelvin. I may have dropped off a Kelvin on a previous problem. Okay, and so then we would know for that one that T of the boundary would be 275. Okay, so let's start filling in. Let me just see, nope, I did that right. Aha, I did forget it. So over here, kilogram Kelvin. Okay. All right, so let's start thinking about what we need to do. A, we need to find heat transfer. So that is automatically, we're thinking we've got all this information. That's kind of a review problem. So we're going to start with A, And the equation that we're going to use for that, I am standing right in front of it. See if I can duck down. So the equation we'll use, again, as always, we'll start with energy rate balance. And remember that in this case we have two flows, so we need to include both M1 and everything pertaining to it, so that's state 1 and state 2, I mean inlet 1 and exit 2. And then in addition we also have what comes from the second flow, which is the air, inlet 3 and exit 4. Okay, so we know a couple of things. What do we know? We know that it's a heat exchanger. So how much work is done in a heat exchanger? None. So this one goes. We are ignoring KE and PE. And then importantly, we know this one is 170 times M1 dot. And so that's good news because then all we have left is Q dot, M1 dot, and our enthalpy, all our 4 different enthalpy values. So let's go ahead and solve for Q dot. And so we'll have M1, that's a 1, sorry, I meant to put the dot there. And because I'm leaving Q on this side and putting everything on the other side, I'm just going to switch the order of everything. So we'll have H2 minus H1 plus M3 dot. Actually, we know what that is. That's 170 M1 dot, so let's go ahead and put that in. Little space as that dries. H4 minus H3. And then again, we're going to just divide through by M1 dot, because that would be, what do we want? We're trying to evaluate the rate of heat, where do we go? Evaluate the rate of heat transfer in kilojoule per kilogram of water flowing. So that's important to know which mass rate it's with regard to. So it's with regard to M1 in this case. So I'm going to divide through by M1. So that drops out, and that drops out. So now I just need to find all of my enthalpy values, and then go ahead and drop them into the equation. So I'm going to just jot down what these are. So this is 2675.5 kilojoule per kilogram. The rest will have the same units, so I'm going to leave them off. So interestingly, that one we know is water vapor. What about this one? Well, here we need to take a look. We need to see what it is. So I'm going to start with the pressure table A3. So A3, we're going to start with 1 bar, and we see 99 degrees. We're sitting at 20 degrees. So clearly a supercooled liquid. So that means in absence of, we don't have enough information, so what we can do then is to use just the fluid value, the saturated fluid value. So that's what we will use. So saturated fluid value at that temperature. Let's see if I have space, and that's going to be 83.96. And then I have, I guess I didn't write it in my notes. Oh, so what I opted to do instead then is for this one, instead of looking up in the table, which I could, I opted to use C sub P times the change in temperature. So here I'm going to have H2 minus H1 plus 170 times C sub P T4 minus T3. So dropping in all those values, can you see? No. There we go. So again, what I've done is I've written my energy rate balance equation. Go ahead and divide it through by M1 dot. That's the proper flow rate that I'm interested in comparing against. So everything cancels. So I'm left with H2 minus H1 plus 170. And then for this, I decided to use C sub P times the change in temperature. So that's easy enough. And then, and the reason why that is actually a very reasonable thing to do is that this is only very slightly different. So if I look at the C sub P values, they are dramatically the same between these two. When the temperatures are much further apart, then we have a problem because then the C sub P value varies a lot. And so that's where we end up with more error coming out of this way of doing things. Okay, so now I'm going to drop in all of the values. And this is in kilojoule per kilogram, so that's good news. 170, C sub P, 1.005 kilojoule per kilogram Kelvin. Change in temperature, 290 minus 275. So Kelvins cancel. And so altogether, final answer is equal to negative 28.8 kilojoule per kilogram of water flowing, saturated vapor. Okay, so hopefully that is okay. So just remember with heat exchanger that we have two pairs of inlet and exit. And so that means we have to have a component for each one in our energy rate balance equation. All right, so let's look at part B. So again, this is number 106, part B. All right, and here we are looking for entropy production. And again, here we have expanded our control volume. Remember, you can set your control volume however you like. So we've expanded our control volume to be slightly bigger than the heat exchanger so that we now know what that boundary temperature is. It's just the ambient temperature. And so we're going to remember that we're using T sub B is equal to 275 Kelvin. Okay, so we have our energy rate balance, our entropy rate balance. I'm going to go ahead, I've already solved it for the entropy itself. And I'm going to go ahead and drop in for M3 dot, I'm going to go ahead and put in M1 dot times 170. All right, so what do I know? I'm going to use this one for water from the tables, because I have steam tables, so I could do that. Sorry, I'm standing right in front. And then for this one, we're going to use ideal gas equation. And that one's going to have temperature and pressure. So we have all the components we need for that. Okay, so let's come back over here. I need to fill in a few values. So here we need to add in our entropy values that we get from the table. So 7.3594 kilojoule per kilogram Kelvin. Same units for S2. We're going to do the same thing that we did for the enthalpy. We're just going to use the saturated fluid value. So S sub F of T2. And so when we get that, we get 0.2966. Okay, so these are the values we're going to need to plug in for the equation for entropy production. And so what else do we need to know? I think that's everything. Because R is 0.2870 like it usually is. Go ahead and write that in here. R is equal to 0.2870 kilojoule per kilogram Kelvin. All right, so now we have everything there. All right, so we'll go ahead and plug everything in. And so negative 28.79 kilojoule per kilogram times 1/275 Kelvin minus, oh, we forgot to divide. So I am again trying to find this value. So I'm going to divide everything by M1 dot. So good news, that drops out. That drops out. This is what, this right here is what I'm trying to find, and then Q dot over M dot is what I actually have. All right, so that's good news. So now I'm going to switch this, instead of saying minus S1 minus S2, I'm just going to flip the order and say plus S2 minus S1. So plus S2 minus S1 kilojoule per kilogram Kelvin. And then I'm going to add this plus 170 times, and so now I'm going to use the ideal gas equation like we had before. Oh, I should have written that out, and I did not. So what I'm going to, that equation that I'm going to use, it's the same one we used before. Let me jot it up here. C sub P ln T4 over T3. Can you see? Yes. Minus R ln P4 over P3. Okay, so so let's finish that up. So then 1.005 ln 290 over 275 minus 0.2870. Oh, I missed some units. Boy, I've had a little bit of trouble tonight. So this will have no units, and neither will the next one. C sub P and R are both in kilogram per, kilojoule per kilogram Kelvin, so I'll add that at the end. Ln 1 over 1 kilojoule per kilogram Kelvin. Ln of 1 is 0, so that term drops out. And so altogether we get 2.1157, or entropy production in kilojoule per kilogram Kelvin of 2.12 kilojoule per kilogram Kelvin. Okay, so again, pretty straightforward. Some of this was review, particularly looking at just open systems like this. This should have been reviewed. That should feel comfortable. Again, the kilojoule per kilogram, that's a slightly different setup that now we know how to handle. And then what's new is looking at entropy production. We have an entropy rate balance equation and an entropy balance equation for closed systems. So those work pretty much like the energy rate balance equations. And so the only other thing that we can do is that anytime we have an ideal gas, we can use something like that. And again, that works best when the change in temperature is not very great, so that C sub P is approximately constant. Okay, so I think that's it.